Hello, everyone. Good morning, good afternoon, good evening, wherever you are calling from. My name is Siva Angappan. I'm the Director of Process Engineering for Headworks. I'm joined by Afnan Din today. He's the Vice President for Biological Divisions. So we're going to talk about retrofitting, upgrading existing wastewater treatment systems today with the MBBR and IFAS technology. Our contact information is shown in the slide, so feel free to contact us for any project needs. So today's agenda is the introduction. First is introduction to MBBR IFAS, then the benefits of MBBR IFAS technologies, and the drivers. Why would you do retrofit or upgrade, and the challenges of upgrades and retrofits, and then a few case studies of actual upgrades and retrofits. Headworks has a global footprint. We have projects biological treatment systems projects around the world with more than 50 countries in the world. And we have more than 200 installations of MBBR IFAS around the world. We have projects or installations in 20 different industries, and then domestic commercial type projects where we do treatment systems for cruise ships, hotels, amusement parks, all those kind of things. So biological treatment systems can be divided into two broad classifications. One is the suspended growth, which includes active sludge, and the other is attached growth. Within attached growth, we have static fixed film, which is like a trickling filter, or a dynamic fixed film, like a RBC, or rotating biological contractors. So MBBR is the latest innovation in the dynamic fixed film area, where the media is completely mixed and continuously mixed, and it's also handles continuous flow. So that's the newest dynamics fixed film technology. It's been in existence for more than 20 years now. So Headworks was one of the pioneers developing this technology, right from the lab studies to pilot studies to commercialization. The attached growth can be combined with suspended growth, like an active sludge plant. And then we can combine them into a single technology called IFAS, which has both suspended growth and attached growth in the same tank, which can shrink the footprint quite a bit. So fixed film technologies are, you have seen trickling filters or rotating biological contractors shown in the top. So this is the MBBR is the latest adaptation of this fixed film technologies, which is much more efficient and then trouble-free operation. The media is a place to grow biofilm. You can see the biofilm, different types of biofilm there. The one you see on the left are the BOD heterotrophic bacteria biofilm, which is grayish and brownish, whereas the one on the right is the reddish, and it's nitrification biofilm. It can also be used for denitrification using the anoxic process. That will be similar to heterotrophic bacteria biofilm. The MBBR and IFAS process can be customized whichever way you want. You can do it only for BOD removal, or only for nitrification, or only for post-denitrification, or combination of all of those. We can add any of these processes to an existing process as an upgrade, or we can retrofit the existing process to add any of these processes. So in summary, we can do any of the BOD removal, nitrification, denitrification, or even phosphorus removal using the MBBR IFAS technologies within the existing tanks, either as an add-on to the back end or front end of the existing process, or complete retrofit of the existing processes. So why you do biofilm based process is that the biomass in the reactor or on the media is self-regulating. What that means is that the operator does not need to control any of the operating parameters within the tank. You don't need to control RAS, you don't need to control MLSS, and it's a single pass treatment in the MBBR only. In an IFAS process, the sludge will be recycled, but in an MBBR process, the treatment is single pass. The water goes in, water goes out. You don't have to control any of the parameters in the tank except DO. So the design is flexible so that you can upgrade part of the systems or entire system. within the existing reactors. You can do part of the system retrofit by separating a portion of the reactor and converting it to a biofilm-based process, or you can do the entire tank. Minimal operator adjustment, as I said earlier, in an MBBR process, you don't need to control MLSs, you don't need to control RAS or recycle. And what you do need is equipment maintenance outside the reactor. So nothing inside the reactor needs maintenance over 20, 30 years. So whatever you put in, we put in the reactor, like a media, aeration grid, or media retention screens. They have a lifetime of 20 to 30 years. So no maintenance or empty in the tank is required for 30 years. It's stable under large load variations. When you have a highly variable flow or loads, the biofilm on the media will shrink and grow depending on the load. So you don't have to manually adjust any parameters. If the load is increasing, the biofilm will automatically grow. And when the load is decreasing, it will decrease to match the load coming in. The most important thing is smaller footprint. If you are building a brand new greenfield site, wastewater treatment plant, MBBR can save up to 50 to 75% of the space relative to active sludge. IFAS will also save similar amount of space. In an IFAS system, you will be having a large clarifier similar to active sludge. So the space requirement for IFAS will be similar to MBBR, but both of them will have 50 to 75% less space than active sludge plant. So the design parameters we use are very similar to active sludge parameters. The DO, alkalinity, loading rates. In an integrated fixed film, we combine the active sludge and biofilm design factors. In a biofilm process for BOD removal, we might need only 2 hours of retention time for BOD removal in a municipal wastewater. Whereas for nitrification, we'll probably need another 2 to 3 hours. Whereas activated sludge will require anywhere from 12 to 24 hours of retention time to complete nitrification and increase SRT and HRT as well. So as you can see, we can do 4 to 6 hours of retention time for BOD and ammonia removal, whereas an activated sludge will require 12 to 24 hours. You can imagine the footprint savings by using the biofilm processes. The one additional design parameter we use is the loading rates on the media, what we call surface area loading rate. For high rate processes, for BOD only removal process, we use a high rate of 15 to 25 grams of BOD per square meter of internal protected surface area on the media per day. So one point is that we don't use the external surface area of the media in our design. So we have noticed that we don't grow any biofilm on the external surface area. So we use only the internal protected surface area. In a nitrification process, we can use a loading rate of 0.5 to 1.5 grams of ammonia nitrogen per meter square per day. Typically, for our autotrophic process, we need about 40, 50 milligrams of alkalinity. And for combination of heterotrophic, autotrophic bacteria, where BOD and ammonia are removed, we need about 75 milligrams of calcium carbonate alkalinity. So the difference between MBBR and IFAS is that the main difference in schematically is the only difference is that you recycle the sludge. But in process-wise, there's quite a bit of difference. In an MBBR process, it's a single pass shown on the right, so no RAS is there. So the design is entirely based on biofilm in terms of surface area loading rates and retention time. On the left side, you have the integrated fixed film process where we recycle the sludge. In that case, we design 2 processes at the same time, activated sludge for the suspended growth and attached growth for the biofilm MBBR process. We combine them into a single process. So in an IFAS process, there will be generally a loose control of the MLSS, which is highly variable. You don't have to have tight control of the MLSS like an activated sludge plant. We can vary the MLSS between 2,000 and 3,500, but generally we design at the MLSS of 2,000 so that your clarifier is not overloaded with solids. So if you're using existing infrastructure, for example, your clarifier we can still use your existing clarifiers, but we can offload the clarifier of the solids loading. We can reduce the MLSS in the IFAS system so that your clarifier is still can be used. We can also periodically we can vary the MLSS to match the loading rate, but the most of the load variations is taken care of by the biofilm. So the activated sludge is basically a support process in an IFAS process. So the design is still MBBR design with support from IFAS design. So the advantage of the IFAS process is that if we have an activated sludge plant, we can easily retrofit them using the existing tanks. The clarifier is already existing. The tanks can be divided, or if you are doing only BOD nitrification, you don't have to divide the tanks. We can use the existing tanks as long as you meet the design parameters like flow velocity and approach velocity and hydraulic requirements. So to simplify the process, if you are doing only BOD only right now, we can add nitrification within the existing tank, and we can use the existing tank without any modification other than adding the aeration requirement as well as the media retention screens. And we can increase the flow as well, as long as your clarifier can handle the hydraulic, and it can handle much higher solids loading in the reactor and the clarifier because we are reducing the MLSS from the previous activated sludge. So we can reduce the solids loading, we can increase the flow throughput, and we can meet new requirements like ammonia or total nitrogen within the same tanks. Even if you are doing only BOD removal within the same footprint of the activated sludge, we can add nitrification, denitrification, even phosphorus removal, all in the same footprint, same tanks, within the same clarifiers. So the drivers are, why would you choose one versus other? MBBR is ideally suited for as an add-on process if you don't want to disturb the existing processes and you still want to upgrade your system. So for example, if you are doing only BOD removal in activated sludge plant, you want to add nitrification, we can add it as a post-nitrification step even after the clarifier so that you don't have to handle the nitrified wastewater in the clarifier. So we can leave the existing system as is and then add a post-nitrification because the nitrification in a municipal wastewater does not add much solids. So 1 milligram of ammonia nitrogen will add only 0.1 milligram of TSS. So if we are nitrifying 30 milligrams of ammonia, for example, you will generate only 3 milligrams of TSS. So it's not something you need to remove after the nitrification process. So we have done a number of processes where we added a process after the activated sludge system for nitrification or even denitrification. Or if you are upgrading a fixed film system like a trickling filter or RBCs, we can add the MBBR process within the same tanks. So the operators are already familiar with the fixed film processes. They can easily adjust to the new process. Whereas IFAS is more suitable for existing activated sludge systems, and you want to either upgrade or retrofit, completely retrofit. So you can retrofit to handle increased flows and loads, or we can upgrade them to do more processes like nitrification, denitrification within the existing tanks. Depending on the process you use, if you use BOD only or BOD on nitrification, we don't have to divide the tanks into multiple tanks. We can use the existing tanks. If you are adding denitrification, then you have to separate one tank out of the existing tank to make it an anoxic process. Again, if you are adding phosphorus removal for biological nutrient removal, we can add that too with an anaerobic process upfront. Overall, both processes are low carbon footprint. You don't generate more carbon because of construction or any other things, and you don't require more energy for aeration. It will be same as activated sludge system. So the benefits of the retrofit or upgrade is that you can, if you have a site constraints, you don't have to take up new space or new tanks, new construction. You don't need all that. And then the resiliency of the biofilm process, which can handle toxic loads, toxic shocks, highly variable loads, and it's easy to upgrade as the population loads increase gradually in a modular format. If you predict that your load is going to increase 10% every 2 years, for example, we can retrofit only how much you need to handle the extra 10% load in the first 2 years. And again, add more load another 2 years. So you can do all the phased approach using the IFAS MBBR retrofits. You don't have to spend all the money upfront to upgrade your system. You can do in phases. So in terms of footprint comparison, as I mentioned, it's when you do MBBR and DAF, it's much more compact. It's a very small footprint, and it's more suitable for smaller flows under 5 MLD or 1 MGD, or industrial plants where they don't have much footprint and they want pretty much completely operator-free operation. So when you use an MBBR plus DAF with some automatic controls, you don't have to have an operator monitoring the system continuously. And compared to Activator Sludge and Clarifier, the footprint is very low, like 10 to 20% of the Activator Sludge Clarifier. If you're using the MBBR plus Clarifier, which is basically an IFAS process, you can save the footprint by half or more relative to Activator Sludge. So these are the different types of media we use. The Active Cell 450 in the bottom was our original media. This was invented in the late 1990s. And then since then, we made improvements to the media. We have recently added another media called Active Cell 1200, which has 800 square meters of internal surface protected surface area per cubic meter. So each media has its own application, but we design based on the requirements for loading rate and removal rate. Generally speaking, if you have an industrial wastewater with highly refractory substances like a high COD to BOD ratio, for example, you would use the Active Cell 450. If you have a high temperature industrial application, you will use that. The Active Cell 450 can handle up to 45 grams of BOD per square meter per day. So that can handle highly variable loads as well. And if you are using really low load or cold temperatures or nitrification only, those kind of processes, we would use Active Cell 920 or Active Cell 1200. It's all, generally speaking, we can use any of the media for any of the processes, but we have some guidelines depending on the operating parameters like temperature and loading rates. So typically, we provide a minimum level of scope supply plus add-ons. So the minimum internal protected proprietary equipment we supply are the media, aeration grade, media retention screens, and anoxic zone mixers. We need this minimum level of scope of supply to guarantee the process. So anything outside of the reactor, for example, blowers, pumps, can be supplied by us or can be supplied by the customer. Same thing with control systems, instrumentation. We can provide either complete turnkey system, including all the equipment, or we can take care of the technology part and guarantee the process and supply only what's required for the process in the reactor. So I will pass on to Afna and Din, who will present some case studies, and then I will present a couple of case studies in North America. Then we'll conclude after that. Afna?
Thank you, Siva. Siva, shall I share my slides instead so I can control it? So plant upgrades and retrofits. I look at some of the drivers for upgrades and retrofits so you can understand why there's a huge demand for upgrading and retrofitting existing plants. The first one is obviously a shortfall in treatment capacity. You see this all the time with population growths. Capacities of treatment plants are always limited and they need to be increased. The other is an improvement in effluent quality. So tighter regulations, tighter permits, consents require treatment plants to be upgraded or retrofitted to meet tight limits. Most often there's limited space. So constructing a new treatment plant or additional lanes is not always easy because of limited space. And the other final advantage is the low cost versus new build. So retrofitting plants is clearly low capital cost versus building a new plant. There are obviously challenges. So when you retrofit plants, there are some challenges which we need to overcome. The first challenge is often we need to keep the existing plant running during the retrofit. Sometimes you are fortunate, you have multiple lanes, like 5 or 6 lanes, and you can take one lane out of service and carry out a retrofit 1 lane at a time. But sometimes you only have 2 lanes. So you need to keep the existing plant running during the retrofit. So we'll touch on how we do that. Temporary treatment solutions. So sometimes we need to provide a temporary treatment solution to still meet the effluent limits while we're carrying out a retrofit. And there are also design challenges. So when you're retrofitting existing plants, there are some design challenges that we need to consider and take care in our design. So really touching on further what Siva explained about IFAS and the advantage of IFAS. Clearly, IFAS is a hybrid process. It's a process which combines suspended growth and attached growth. And one of its main advantages is the ability to retrofit existing conventional activated sludge plants to increase capacity or improve effluent quality. So what you have here is a very good example, a very common example of a conventional activated sludge plant with an existing aeration tank and a final clarifier. If you had to increase the treatment capacity, you would typically have to expand the aeration tanks. You will have to provide additional aeration lanes. Whereas with an IFAS, what we're doing is we're maximizing the use of existing asset. We are adding carriers with high surface area inside the existing aeration tank. This high surface area carriers increase the specific surface area while keeping the total overall volume of the tank the same and the area the same. So in essence, what we're doing is we're providing space for biofilm to grow on the carrier, and this is increasing the volume of biofilm, biomass equivalent. The total volume of bacteria inside that aeration tank is 4 or 5 times more versus a conventional activated sludge because we've added carriers inside the aeration lane. By doing so, we're allowed to treat mostly 40 to 50% more in capacity. I would add here, the limitation is normally the hydraulic limitation, not the treatment capacity, which is the limitation. Typically, we could go up maybe 2-3 times, but because of the hydraulic limitations of existing plants, normally we can increase capacity either double or 50% more. Here's another example. This is a real life example where we retrofitted an existing activated sludge plant that was designed for 10,000 cubic meters per day, achieving a BOD of less than 20 milligram per liter. And that same activated sludge plant, we were able to increase the capacity by 50%. So the same activated sludge plant was retrofitted with 2 zones, one for BOD removal, one for nitrification. Unlike activated sludge systems, an attached growth process, typically we separate the BOD zone and the nitrification zone. So we have 2 separate zones. And you see, as you see in the bottom diagram, we've created 2 zones. The first zone is for oxidation and the second zone is for nitrification. So by creating these 2 zones, adding carriers inside, we've increased the equivalent mixed liquor suspended solids concentration. And that allows us to treat more load and achieve nitrification in that same tank volume. So that's the key to why we're able to increase capacities of existing activated sludge plants. This is another example where we're trying to demonstrate that with an existing activated sludge plant, you can not only achieve nitrification by retrofitting, but you can achieve denitrification. You can achieve various TN limits, less than 10, less than 5, ammonia less than 1. And here is a good example where you can see how we've taken an existing activated sludge lane and we've created multiple zones, depending on what we're trying to achieve. So if you're looking to achieve a tight TN limit, you will have a pre-denitrification zone inside the same reactor, followed by a BOD removal zone, followed by nitrification, followed by post-denitrification. So what's happening is, by adding carriers, we're allowing ourselves extra volume to do denitrification. Similarly, you can do BioP removal. So you can take an existing plant and upgrade it to achieve biological P removal. And again, you're adding the carriers, which decreases the tank volume required for your carbonaceous removal and nitrification, which then in turn allows room for BioP and denitrification, all within the same zone. One of the reasons why an attached growth process, like an IFAS process, is a lot more robust than an activated sludge process is the fact the carriers, which retains the biofilm, never leaves the system. So typically what we're doing is we're doing BOD removal in the suspended phase at very low MLSS, around 2,500 milligram per liter. And we're doing nitrification on the attach phase. And we're keeping our nitrifiers inside the tank until they die when they slough off through collisions of the carriers, between the carriers. So your carriers never leave the system. So in essence, what you're getting is a very long sludge age versus conventional nitrifying ASP, because your carriers don't leave the system. Design considerations, it all sounds so perfect, retrofitting plants and increasing capacities, all too good to be true. But there are a lot of design considerations when you're designing retrofits for existing plants. Firstly, an MBBR and IFAS system is a complete mixed reactor. So they cannot be designed as plug flow reactors. And that's something that you will see how we retrofitted a plug flow reactor into a complete mixed reactor in one of the case studies. But that's an important consideration, because in a plug flow reactor, the approach velocities are typically too high. And what we mean by the approach velocity is we mean the floor velocity, the flow into the reactor across the cross-sectional area. So if the approach velocity is too high, the carriers would migrate towards the end of the reactor. So the approach velocity is an important consideration when you're designing for retrofitting plants. You have to review existing air grid layouts if they are to be reused. So we will do that. We look at the existing air grid layout, whether it's fine bubble, coarse bubble. We look at the arrangement. We see if that needs to be rearranged. Hydraulic limitations, these need to always be considered, because increasing capacity, there are two areas you need to look at. One is the treatment capacity, which, as I said earlier, we can sometimes quadruple. If the tanks are like extended aeration, you can quadruple the treatment capacity, but there are hydraulic limitations in the plant. So that needs to always be considered. And the other thing is the retention sieve, the layout and the flux rate on the retention sieves, which prevent the media from escaping from inside the reactor. So the retention sieve layout, how will they be positioned? Where will they be positioned in an existing reactor? All needs to be considered. Installation and commissioning. One of the benefits of the MBBR IFAS process is that there's minimal equipment. There's no mechanical moving parts. We have stainless steel sieves, stainless steel air grids, so which are both, the air grids are maintenance free. The sieves are installed about 0.5 meter below water level, so they're easily accessible, and they are designed to be maintenance free. They're wedge wire screens which protrude out from the effluent wall. The air grids can be retractable as well. I'll show you some photos on where we've supplied retractable air grids, where customers require access to the air grids periodically. To access the air grids, we can provide retractable, retrievable air grids, and which can be taken out with the tank in operation. Typical startup is around 4 weeks, and the media design life is 20 years. So we guarantee the media from any breakage, any the media deforming or anything like that. Temporary treatment solution for treating wastewater while one lane is out of service may be required, and we have looked into how we do that. Often we are able to take a lane out of service, but in some cases where a lane cannot be taken out of service and we need to provide a temporary treatment solution, we can do that. Just to give you show you some photos of some installations, the media is shipped in bags. So 1 cubic meter bags, 2.5 cubic meter bags. You see the retention screens, they're cylindrical with horizontal and vertical supports, wedge wire type. They're installed at the outlet wall of the MBBR IFAS reactor. And you see the aeration grids with the diffusers. These are the retractable, retrievable air grids that we provide. They're constructed, they're built on a frame, and then they're dropped inside the aeration tank and can be easily taken out with the media inside the tank if need be. Typical commissioning phase, we add around 30 centimeters of water above the air grids to carry out some pattern testing first, to check the aeration grid, check the performance of the grid, see if there's even air distribution. We then add the media. The media filling is done. First, we add some clean water, and then we begin to add media. The key here is that we add media over a period of 7 to 10 days. So we don't add media all at once. is batch acclimation of the process of the biofilm. So the startup takes around about 7 days of filling the carriers with the wastewater. So you have to progressively fill the biomedia until it's all wet and it's mixing. Typically, we add return activated sludge for seeding. So the sludge is added for seeding, and then we monitor the DO levels. We add all the media inside the aeration tank, whatever we've designed for, percentage fill, and then we bring in wastewater as food, and we allow for batch acclimation for around 7 days to 10 days before we start seeing biofilm on the carriers. In terms of our case studies, we've got around 200 MBBR IFAS installations worldwide. We've got over 100 municipal installations, and the other being industrial. So we'll focus on some key case studies. These are all retrofits, and we've specifically selected these retrofits because each one of these retrofits demonstrates something unique. Dubai Investment Park was an existing activated sludge plant. It was designed to treat 5,000 cubic meters per day, and we were able to double the capacity to 10,000 cubic meters per day without any additional tanks or civil works. We used all the existing infrastructure. We were able to use the existing clarifiers. So you do not need to increase clarifier capacity. And the reason you don't need to increase the clarifier capacity, because when we double the capacity of an activated sludge plant, we're in essence lowering the solids loading rate onto the clarifier. And we're doing that by reducing the MLSS. So the original activated sludge plant was operating at around 4,000 milligram per litre. Once we doubled the capacity with carriers, we reduced the MLSS to 2,000 milligram per litre in the suspended phase. And in the attached phase, the solids are very, very minimal. So it's around 200 milligram per litre. And the plant was able to achieve BOD removal and nitrification. Originally, it was only designed for BOD removal, and it's now achieving ammonia less than 1. I will show you a video here. I hope everyone can see it. So this investment park receives flows from offices, small industries, retail, business park. So different types of wastewater oil feeds. This is the carriers. Carriers are shipped in bags, as I said. This was a glass line still existing tank, which we retrofitted with air grids and retention sieves. As you can see in the video here, sorry, I'll just pause this. We were able to install sieves in a GLS tank. So it's easier to install sieves in a rectangular concrete basin, but we were able to do the same in a circular tank as well, with specifically unique designed supports. So we have a lot of experience in retrofitting plants with different tanks, different configurations. These are the air grids that supplies the air for oxidation and the air for mixing. These are the retention sieves, which are wedge wire. You have the blowers at the back. So our scope in this was the whole process design. We supplied the aeration grids, the retention screens, and the carriers. This is active cell 450 media being loaded into the tank. And as you can see during startup, the media takes a couple of days before it starts to mix. Due to the properties of high density polyethylene, the media needs to be completely wet before you get complete mixing. So this is during startup. We're filling the tank. That's seeded sludge being introduced into the tank for startup. So this existing plant was for 5,000 cubic meters per day, achieving BOD removal only, upgraded to achieve 10,000, to treat 10,000 cubic meters per day to achieve full nitrification, ammonia less than 1. The next project I'll talk about is an oxidation ditch upgrade, which is an interesting one. Here we were able to increase the treatment capacity by 40%. The limitation here was the hydraulic limitation, and the limitation in the clarifier capacity. So what we do is we don't just look at the biological treatment capacity, we look at the overall capacity of an existing plant and how we would retrofit the entire process, not just the biological treatment capacity. So although we could increase the capacity of the biological treatment stage a lot more, we were limited by the hydraulic limitations in the clarifier. In this plant, there were 4 activated sludge lanes. 2 were oxidation ditches, carousel tank, plug flow reactors, and the other 2 were standard rectangular aeration basins. So the existing flow was 20,000 cubic meters per day, number of trains were 4, and we were able to increase the capacity by 40% to treat 28,000 cubic meters per day. Typical raw wastewater characteristics was a BOD between 300 to 450 milligram per litre, TSS 350 to 400 milligram per litre, and ammonia up to 45 milligram per litre. And we had to achieve BOD less than 10 milligrams per litre and TSS, and ammonia less than 5. What we did here, we created 4 small zones inside the existing aeration tanks. These zones are called MBBR roughing reactors. So what these are high rate MBBR roughing reactors. This is one of the unique advantage of MBBR IFAS. It can be applied in many different ways in an existing tank arrangement. You can create small zones, you can put the media in the full tank. There's a lot of flexibility on how you carry out the retrofit. So what we did here, we created very small zones at the front end of the existing basin. And these zones act as high rate reactors. They're filled with up to 70% media with a retention time of around an hour and a half. And these reactors are able to remove the bulk of the BOD coming into the tank. So we're talking around 70% removal you can achieve in that small high rate zone. That then creates volume in the remaining reactor for you to achieve nitrification in a suspended phase system. So we left the remaining aeration tank as is. We didn't touch the aeration tank apart from the front zone. And that was important because you have an oxidation ditch, which is a plug flow reactor. So we didn't want to go in and demolish the whole tank and start demolishing all the walls. We wanted to have minimal changes in the existing reactor to be able to do that. There were many options which we considered. And the reason we went for this one was because it was the most easiest to implement with minimal changes to the existing tank. And here you sort of see the GA, the layout of the carousel tank. So what we did, we actually created a very small zone at the front end of the carousel lane. This is a complete mixed reactor. We changed we kept the existing inlet as it was, and we created a baffle wall to create that zone. And we just changed the direction of the flow from the outlet of the MBBR zone. And the remaining tank, the remaining carousel lane remains as is. Nothing was changed. The effluent weir remained as is, the existing inlet, existing RAS. It was just this new wall that was created. Whereas where it says new wall, that was created. That's all. And then we went into that zone and we retrofitted that little zone. The rectangular aeration lane was a lot more simpler to do because you don't have the challenge of a plug flow problem there. And here you can see, maybe if you look closely at the bottom left where it says the top view, you can see the zone on the left side. And these are the sieves on the outlet wall, and the water would pass through the sieves into the remaining carousel tank. There you can see it operational. We do supply drain sieves as well. So drain sieves are, in the event you ever need to drain the tank, you can drain the tank and leave the media inside and then take the media out. But you can drain the tank. So drain sieves are provided to allow you to do that. Some real sort of advantages of upgrading this specific plant was we maximize the use of existing assets. We increased the flow capacity by 40%, minimal civil works. We produce a consistent effluent of 10-10-5. It's very reliable and it's very less in terms of operator involvement, in terms of operator control. There's no maintenance required. You have a DO control only. That's it. And the effluent was used for irrigation from this plant. So it's 100% reused. I'll pass over to Siva to discuss and share with you the 2 case studies from North America.
Yeah, so Batesville, Arkansas is a small town in Arkansas with a population of less than 20,000, but the wastewater they generate is equivalent to 100,000 people. The reason is that they have a lot of industries, poultry, bakery, food processing. So all those industries, they send the wastewater pre-treated to the wastewater treatment plant. So they generally pre-treat only BOD up to 250 milligrams per liter. Then any nitrogen has to be removed by the municipal wastewater plant. So the existing plant was a lagoon treatment system. It's a large lagoon, maybe 20 acres of lagoons, but they were given a new nitrification limit. So the operators were not familiar with the active sludge plants, so they didn't want to take on new responsibilities in terms of controlling MLSs, RAS, all those things, and they didn't want to hire new operators either. So they wanted to, I guess, install a small, easy to operate, simple process. So we provided an option to install the MBBR system after the lagoon. What happened was, due to the increasing flows and loads, their wastewater kept increasing in loads, especially nitrogen. So in winter, they were not able to meet even the BOD limits. So the BOD coming out of the lagoons were about 50, 60 milligrams per liter after the lagoon, just for winter. In summer, they were able to remove BOD and nitrogen, ammonia nitrogen, all of them to meet the limits. So they really needed a system that can flexibly run as the load comes in, it has to treat, and as the load goes away, it still had to run. So MBBR was the ideal process, and we added a small MBBR reactor 2-train system in the back end after the lagoon to handle 10.8 mgd, which is like 40 mld. And the temperature has to be as low as 5 degrees C or less. So in winter, what happens is that the lagoon, because of the retention time in the lagoons, the wastewater reaches very low temperatures, almost reaching the freezing level of temperature. So that wastewater, the MBBR treatment system should be able to handle temperature as low as 5 degrees centigrade or up to 20-25 degrees centigrade. So these are the parameters given to us. Handle variable loads, handle wide range of temperature, handle with no BOD or with the high BOD, or no ammonia or high ammonia. So these are the constraints we had to start with the design with. So we designed a system, 2-train system with 2 reactors. The first reactor is for BOD polishing, and the second reactor is for ammonia nitrification. So you can see the flow is highly variable. In winter, peak of winter, the flow is quite low. In the rainy seasons, in the early winter and the summer, the flow is very high. The temperature is, again, after the lagoon is quite variable. 20 C in summer and 5 C or even less in winter. You can see ammonia concentrations is shown in the blue dots, is the coming into the MBBR. That can be 0 in summer and most of the year. And in winter, it shoots up to 30-35 milligrams per liter. The MBBR has to adjust really quickly to this condition. In addition, as the ammonia concentration increases, the temperature also drops. So you have 2 different impacts. Your kinetics are slowing down because of the drop in temperature, as well as the MBBR has to handle the high load of the ammonia at the same time. So you can see the results from the MBBR before and after. The blue dots are before, and ammonia concentration are shown in the green. They are constant throughout the season and throughout the year. So that's because of the biofilm can shrink and grow depending on the conditions. And one point about the temperature is that the nitrification process in a biofilm is not very sensitive to temperature. The nitrification performance is same throughout the year, regardless of the temperature. That's because of the protected surface area in the media. Within the surface area of the media, the biofilm has hundreds of layers. The bottom layer is strongly attached to the media, and because of the metabolism of the bacteria, the bottom layer is actually very warm. Only the top layer is cold of the biofilm. The bottom layer is close to 20 degrees centigrade, regardless of the wastewater temperature. That's the reason nitrification performance does not vary with temperature. Moorhead, Minnesota is a similar plant. It's located in a very cold location in Minnesota, especially in winter. So they had an existing activated sludge, Purox activated sludge system shown in the foreground here. 25 years ago, they used this polishing ponds to polish the BOD. And in 2001, they were given a new ammonia limit, not just BOD limit. So they had to install a new process. They were initially thinking of using the pond, but as you know, the ponds are very cold in winter. It can freeze, actually the top layers of the pond freeze in winter. So that's not suitable for nitrification process. So we installed a new MBBR process, small MBBR reactor, which has a retention time of only 4 hours. And similar to Batesville, this also does BOD polishing. So this is a post-clarifier process. So you don't have any clarifier after the nitrification. So whatever TSS you generate is generally between, in summer, it's only 3 milliamps per liter. In winter, as the BOD comes in, it can generate up to 10 to 20 milliamps of TSS in the nitrification reactor because it's also polishing BOD. So that it's within their limits. So they only have to put a solid separation process after the MBBR. Again, it's very cold outside. Ambient can be minus 35 to minus 45 in winter. The MBBR works very well. So you can see the temperature goes down as low as 4 degrees C to 20 C. Temperature is not as cold you would expect at freezing because it's following the Purox plant. So in winter, the wastewater actually freezes in the pond, but because it's coming from the Purox plant, active sludge plant, it's quite a bit warmer. So we designed for 5 degrees C. Process works very well now. So the blue lines are the wastewater flow. As you can see, from January 1st at the 0 to December 31st, the flow is highly variable. Around March, the snow in the city melts on the roads and everywhere. So because of the combined sewer, all the snow melt coming to the plant, and that makes it very cold. So the flow is highly variable because of the snow melt. And the other two peaks are during the rainy season. The flow can vary from 3 to 9 MGD. 9 10 MGD, and the MBBR still performs without any effect on the performance of the MBBR. You can see the ammonia coming in and coming out. It's fairly stable throughout the year, meeting their limits. This is a close look between January 1st to April 30, the peak of the winter. As you can see, the flow spike due to snow melt from the roads. And you'll see the ammonia concentration on the gray, highly variable, sometimes as high as 60 milligrams per liter because of the existing Purox plant cannot handle high loads of ammonia during winter. And the effluent ammonia is fairly constant throughout the winter season. So these charts give you the two main advantages of the MBBR process. It's not sensitive to temperature. The ammonia nitrification kinetics is not sensitive to temperature. The other thing is highly variable loads and flows it can handle, the MBBR process handle without any effect on the effluent of the MBBR. Now back to Afnan, he will discuss the Mubarak project in Egypt.
I'll go through this pretty quickly. I am conscious of the time. So Mubarak wastewater treatment plant was an existing membrane bioreactor. Again, I've specifically shown this slide so that I can demonstrate how we retrofitted an existing membrane bioreactor, which was causing problems for the customer in terms of high operation and maintenance. The membranes kept fouling. So the customer was looking for a small footprint solution, a solution which would fit within the existing membrane bioreactor layout. So we were able to replace the membranes and create 2 streams of MBBR followed by a horizontal flow clarifier. So all within the same volume. Obviously, partition walls were created, but we would try to use the overall footprint remain the same and the outer walls remain the same. The internal walls were created to create 2 MBBR reactors, 2 trains, and we were able to retrofit the same plant with MBBR. I'll show you just a video here so you can sort of see some photos of how the media was installed, the air grids, etc. This is AC920 carrier. This is 680 meters squared per cubic meter. The fact that we have 4 different carriers, we're able to select the right carrier for the retrofit. So depending on what we're trying to achieve, whether it's BOD, whether it's a high rate reactor, whether it's nitrification, we have carriers ranging from 400 to 800 meters squared per cubic meter. The retention sieves, again, on the outlet wall, horizontal, vertical supports. They're cylindrical, they protrude out, they have minimal head loss. So there's less risk of these clogging, choking, which is a problem with flat screens. So we don't use flat screens. The media drops into the aeration tank, really easy to sort of unload. And you can sort of see here how the media bag is unloaded. Each bag contains around 2.5 cubic meters of media. And this plant's been in operation for over 10 years now. And the biofilm only grows in the inside. That's important. So the biofilm layer grows in the inside. That's the layer of the plant once it was retrofitted. I will now share with you an upgrade of a plant in Luxor from 13 MLD to 25 MLD. This is still at feasibility stage, but it really sort of shows you how we've innovated in terms of finding a solution to retrofit the plant. So this was the existing lanes, phase 1, phase 2, and it's designed for 13,000 cubic meters per day, both phases, and we wanted to upgrade to 25,000. We're able to do that by just retrofitting one clarifier, primary clarifier. So on this plant, you have 3 primary clarifiers, 4 secondary trickling filters, and followed by 4 secondary clarifiers. We would keep the 4 secondary clarifiers as is, and we will only retrofit 1 primary clarifier into an MBBR, and we're able to treat 25,000 cubic meters per day. So just 1 clarifier has that volume needed to retrofit with MBBR. And this was the existing primary clarifier, and it sort of shows how we would increase the capacity to approximately 20 to 25,000 cubic meters per day by retrofitting it into a IFAS reactor. And what we're really doing here is, as you see, we've taken the existing existing primary clarifier and retrofitted the primary clarifier with a de-aeration zone in the center column. We've created BOD oxidation nitrification IFAS zone in the center with air grids, retention sieves on the outlet wall, and this is the outlet channel where flows would overflow. And the inlet would come in the peripheral of the clarifier. The flows would flow into the BOD oxidation nitrification zone, through the sieves into the de-aeration zone, and then through the outlet. So it's a very innovative design, but it's just to sort of demonstrate there's a way to retrofit any sort of tank. And we've done very complex, very difficult type of retrofits, but they can be done. And the benefits of retrofits are you don't need to build new tanks. You don't need to have additional construction, additional civil works. So that really sort of brings an end to the presentation. Just before we go into the questions, to add, our presentations are available on our YouTube channel, as are other presentations. So if you want to go through this again or you want to share it with someone, please, you can do. And open to questions, really.
Interesting presentation. With the outlet sieves, I noticed in the very first example, there was a bar seemed to be attached to them, and just wondering how that worked. It was curious. I think it was for helping to remove them.
For the outlet sieves.
Yes.
Yeah, I think they're just supports. They're just horizontal, vertical supports for the sieves. That's all.
Oh, I see. Right.
Yeah.
To handle the hydraulic pressure. Okay.
I had a second quick question. When you mentioned, the hydraulic capacity is typically the restriction. Is that because of the velocities through the plant?
A bit of both. It's the velocities, it's the approach velocities through the plant, but it's more the hydraulic capacity of the plant. So the treatment capacity can be quadrupled or doubled, but the pipe work, the interconnecting pipe work, the clarifier, for example, the sludge treatment, the additional equipment doesn't have the hydraulic capacity, so that would also then needs to be upgraded. And when you start looking at upgrading interconnecting pipe work, then that becomes really costly because you then have to do excavation, etc.
It comes into a picture where we have we're retrofitting active sludge system. So they are designed, as I said earlier, 12 to 24 hours of retention time, whereas we can shrink the footprint quite a bit with 2 to 4 hours of retention time. So when you shrink the footprint, we increase the biomass on the media. So there is no limitation on the treatment of the load itself. But when you have a tank with only 2 hours or 4 hours of retention time, hydraulically it may not be able to handle it because it's based on an active sludge system. If you are starting a brand new MBBR plant, we won't have that limitation. We will design for the hydraulic requirements.
Right. Thank you.
Thank you.
Sorry, I forgot to lower my hand, but I do have a question. You briefly mentioned about a guarantee of the calculations and a warranty of the system.
Mm-hmm. Yeah, so we have 2 different warranties. One is the equipment warranty, which is generally between 1 and 2 years, because most of the equipment are third-party equipment outside of the reactor. Inside the reactors are made by us. The media itself has a lifetime of 20-30 years, but we give a standard warranty of 2 years. Similarly, aeration grid, retention screens, they all have a standard equipment warranty. But the process performance guarantee is more important in terms of how we guarantee the process it will work. So we, depending on the requirements, we will develop a sampling analysis plan during commissioning. And we will give you anywhere between 6 to 12 months to test your process under different conditions, still under the design conditions. Based on the results, we provide the guarantee in advance. Based on the results, we can confirm that the process meets the requirements.
All right, if nobody has any other questions, that was Headworks' presentation. So I thank you all for joining, and we will see you again, hopefully for the next month's webinar.
Thank you, Matt.
Thank you, everyone. Thanks, Matt.
Thank you, everyone.
Thank you, everyone. Good to see you all. Bye-bye.